All right, let's go.
Number 10. Solar power satellites, the first step. Before we get to the truly insane stuff, let's start with something we could theoretically build right now with existing technology. A solar power satellite is exactly what it sounds like, a massive photovoltaic array in geostationary orbit, 36,000 kilometers above Earth, collecting sunlight continuously. No atmosphere blocking it, no night cycle, no clouds, just constant, uninterrupted solar energy 24 hours a day. The collected energy gets converted to microwaves and beams down to receiver stations on the ground. The microwaves pass through clouds and atmosphere and get converted back to electricity at the other end. Japan's space agency, JAXA, has been seriously developing this concept since the 1990s. They demonstrated wireless power transmission in 2015. The technology works. The physics is not speculative. The problem is scale and cost. A Type 1 civilization, one that has fully mastered its planet's energy resources, would build thousands of these, covering the sky in a constellation of power transmitters. The entire planet powered by the sun, with zero emissions, zero fuel, zero combustion. This is not science fiction. It is engineering we understand completely. We just need cheaper access to space. Number 9. Space elevators. The infrastructure that changes everything. Everything humanity has ever launched into space has been thrown there by controlled explosions. Chemical rockets, barely controlled, enormously expensive, catastrophically inefficient. A space elevator changes the equation completely. The concept is simple. A cable anchored to the equator and extending 100,000 kilometers into space, past geostationary orbit. At the end of the cable, a counterweight keeps the whole system under tension. Climbers, vehicles that grip the cable, ride it into orbit. No rocket needed, no explosion, just electricity and a very strong cable. The energy cost of reaching orbit via a space elevator is a fraction of 1% of the energy cost of a rocket. The cable carries cargo continuously, multiple climbers running simultaneously, thousands of tons to orbit per day for the cost of electricity. The engineering challenge is the cable material. It needs to be stronger than any material currently in mass production. The tensile strength required exceeds steel by a factor of 100. Carbon nanotubes discovered in 1991 have the theoretical tensile strength to do it. At laboratory scale, they already exceed the requirement. The problem is manufacturing them at length and scale. We can make carbon nanotubes centimeters long in a lab. We need them tens of thousands of kilometers long. This is a material science problem, not a physics problem. The physics is completely understood. A civilization that solves the materials problem gets access to space at a cost that makes everything else on this list buildable. The space elevator is not just a megastructure, it is the megastructure that enables all the others. Number 8. Rotating space habitats. Living without a planet. The most fundamental problem with long-term space habitation is gravity. Humans evolved in a 1G environment. Remove gravity and the body breaks down. Bone density drops, muscles atrophy, fluid shifts toward the head. Vision degrades from pressure on the optic nerve. After 6 months on the International Space Station, astronauts need months of rehabilitation just to walk normally. The solution is not medication or exercise. The solution is centrifugal force. A rotating cylinder in space creates artificial gravity on its inner surface. The larger the cylinder and the faster it rotates, the closer the effective gravity gets to Earth normal. This is basic Newtonian physics. No exotic matter required, no theoretical speculation. The most famous design is the O'Neill cylinder, proposed by physicist Gerard O'Neill in 1976. 2 counter-rotating cylinders, each 8 kilometers in diameter and 32 kilometers long, interior surface area of over 800 square kilometers per cylinder. Windows running the length of the cylinder allows sunlight in, adjusted by external mirrors. The inner surface is land. The sky is the opposite inner wall. At full rotation, the effective gravity on the inner surface is exactly 1 g. You could live there your entire life and never know you were in space. O'Neill calculated that a pair of these cylinders could comfortably house 10,000 people. Scale up to thousands of cylinders, and you have a civilization living permanently in space without a planet. Some engineers have proposed much larger versions, the McKendree cylinder, 460 kilometers in diameter, with interior surface area comparable to a small continent. The materials required are available in asteroids. The energy required comes from the sun. The physics is completely understood. The only limit is industrial scale and will. Number 7. Asteroid mining operations. The industrial backbone. Every megastructure on this list requires materials, enormous quantities of materials. And lifting those materials from Earth's surface against its gravity well is extraordinarily expensive. The asteroid belt contains the solution. The total mass of the asteroid belt is approximately 4% of the Moon's mass. That sounds small. It is not small. It contains enough iron, nickel, and other metals to build a structure the size of Earth's surface area many times over. A single metallic asteroid, 16 Psyche, is estimated to contain more iron and nickel than humanity has ever mined in all of recorded history. Its estimated value in today's market exceeds the entire global economy by a factor of thousands. An advanced civilization doesn't mine asteroids with humans and pickaxes. It deploys self-replicating robotic systems, machines that mine raw material and use that material to build copies of themselves. Starting from a single self-replicating factory and enough asteroid material, the system expands exponentially. Within decades, a single initial investment becomes an industrial operation of incomprehensible scale. NASA sent the Psyche spacecraft to begin studying the asteroid in 2023. It will arrive in 2029. The first civilization to establish robust asteroid mining operations will have access to material wealth that makes every resource conflict in human history look like a disagreement over pocket change. The rest of this list becomes possible. Number 6. Stellar engines. Moving a star. Here is where we leave near-future engineering and enter the territory of genuinely advanced civilizations. A stellar engine is a megastructure that uses a star's own energy output to generate thrust, moving the star through space, slowly, but moving it. The most discussed design is the Shkadov thruster, proposed by Soviet scientist Leonid Shkadov in 1987. An enormous mirror, roughly the size of a planet, positioned on one side of a star. The mirror reflects a portion of the star's radiation back at it, creating a net force in the opposite direction. The star and the mirror become a single system, slowly accelerating through the galaxy. The numbers involved are staggering. Our sun radiates 3.8 times 10 to the power of 26 watts in all directions. Reflecting even a fraction of that produces real thrust. The acceleration is tiny, but stellar engines operate on timescales of millions of years. Over millions of years, tiny accelerations produce significant velocities. Why would you move a star? To navigate away from a dangerous galactic region, to position your solar system closer to resources, to avoid an approaching stellar collision, to migrate your entire civilization to a more favorable location. A Shkadov thruster requires materials on a planetary scale, but nothing physically impossible. The energy is free, provided by the star itself. A civilization capable of constructing this operates at what physicist Nikolai Kardashev would call a Type 2 level, fully harnessing the energy output of a star. Number 5. Matrioshka Brains. The ultimate computer. A Matrioshka brain is not a habitat, not a power station, not a transportation system. It is a computer, the largest computer physics allows. The concept, named after Russian nesting dolls, is a series of concentric shells around a star. Each shell is a layer of computronium, matter arranged in the most computationally efficient configuration possible. The innermost shell captures the highest energy radiation from the star and uses it to compute, then radiates waste heat outward. The next shell captures that waste heat and computes with it, radiating its own waste heat further out. Layer after layer, extracting every possible computation from every joule of energy the star produces. The computational capacity of a Matrioshka brain around a star like the Sun has been estimated at 10 to the power of 42 operations per second. For context, the human brain performs roughly 10 to the power of 17 operations per second. A Matrioshka brain outperforms the human brain by a factor of 10 to the power of 25. What would you do with that much computation? Run simulations of entire universes, model the behavior of every atom in a galaxy, host the consciousness of every being in your civilization in a virtual reality indistinguishable from physical existence. The Matrioshka brain is the endpoint of computational civilization. A Type 2 civilization that builds one has effectively transcended physical existence. Every mind that ever lived in their civilization can run simultaneously, immortal, inside a single star-sized computer. Number 4. Ringworld, a ring around a star. Larry Niven invented the Ringworld in 1970 as science fiction. Physicists and engineers have spent the decades since asking whether it is physically possible. The answer is complicated. A ringworld is a rigid ring approximately 1 AU in radius, the distance from Earth to the Sun, encircling a star at the orbital distance of a habitable planet. The inner surface rotates to provide centrifugal gravity on its inner surface. The inner surface is habitable land. The numbers are difficult to process. The inner surface area of a ringworld at 1 AU radius is approximately 3 million times the surface area of Earth, 3 million Earths worth of living space on a single structure. The engineering problems are severe. The material must withstand tensile stresses that no known substance can handle. The ring would need to be made of something called skrith, a fictional material with a tensile strength approximately 3 trillion times that of steel. Nothing we know of comes close. The stability problem is worse. A ringworld is gravitationally unstable. Any small perturbation causes it to drift toward the star it encircles. Active attitude control using thruster systems would be required continuously. A true ringworld requires either material science so advanced it approaches magic or a physical understanding we don't yet have. But partial rings, incomplete arcs, and smaller-scale versions face less severe engineering constraints. The concept scales down to something more approachable. Number 3. Dyson Sphere, capturing everything. Freeman Dyson proposed it in 1960, a complete shell surrounding a star, capturing 100% of its energy output. A solid shell at 1 AU would have an inner surface area of approximately 550 million times Earth's surface area. The star's entire energy output, 3.8 times 10 to the power of 26 watts, captured completely, nothing wasted. Dyson himself never proposed a solid shell. He proposed a swarm, thousands of independent solar collectors in various orbits around the star, gradually increasing in number until they collectively intercepted all available sunlight. This is sometimes called a Dyson swarm and is far more physically plausible than a solid sphere. The solid sphere version has a fatal problem. It is gravitationally unstable. A solid shell around a star experiences no net gravitational force from the star, meaning it could drift freely until it made contact with the star itself. You would need active positioning systems covering the entire inner surface simultaneously. A Dyson swarm avoids this. Each element follows its own stable orbit. The energy available to a Dyson Sphere civilization is difficult to comprehend. Our entire global civilization currently uses roughly 2 × 10 to the power of 13 watts. A complete Dyson Sphere captures 3.8 × 10 to the power of 26 watts. That is 10 trillion times more energy than all of human civilization currently uses combined. This is what a Type 2 Kardashev civilization looks like. Number 2. Birch Planet. A shell around a black hole. Paul Birch proposed this in 1991, and it remains the most extreme habitable structure physics permits, short of pure speculation. A Birch Planet is a rigid shell built around a supermassive object, ideally a black hole. The shell rotates. Centrifugal force provides gravity on the outer surface. The black hole's gravity provides the inward force to keep the shell stable. The habitable surface faces outward. You live on the outside of the shell, like living on the outside of a planet, held to the surface by centrifugal force, while the black hole's gravity provides the structural tension that holds the shell together. The energy source is the black hole itself. Matter fed into the black hole releases energy through the accretion disk, with efficiencies approaching 40% of mass energy conversion. Compare this to nuclear fusion at less than 1% mass energy conversion. A black hole power plant is the most efficient energy source permitted by physics, short of matter-antimatter annihilation. The surface area of a Birch Planet built around a stellar mass black hole at comfortable gravity levels would be approximately 200 million times Earth's surface area. Built around a supermassive black hole, the numbers become absurd. Surface areas billions of times Earth's. Energy outputs that dwarf Dyson spheres. The engineering requirements are beyond anything we can currently conceive, but no known law of physics is violated. Number 1. Dyson Sphere around the galactic core, harnessing a galaxy. The Milky Way's center contains a supermassive black hole, Sagittarius A star, with a mass of 4 million suns. Surrounding it is the densest concentration of stars in the galaxy, hundreds of thousands of stars packed into a region just 10 light-years across. A sufficiently advanced civilization, Type 3 on the Kardashev scale, could build a Dyson Sphere not around a single star, but around the entire galactic core, enclosing Sagittarius A star and the surrounding stellar population, capturing the energy output of hundreds of thousands of stars simultaneously, plus the accretion energy from the central black hole. The total energy available from the galactic core region dwarfs any single stellar Dyson Sphere by a factor that is genuinely difficult to express in human terms. This is what a Type 3 civilization looks like, a civilization that has moved from harnessing one star to harnessing the core of an entire galaxy. The Fermi paradox gets interesting here. A structure of this scale, visible across millions of light-years, would be unmistakable. The galactic core would go dark. Its infrared signature would change dramatically. We have instruments capable of detecting this. We have looked. We have found nothing. Either no civilization in our galaxy has reached this level, or they have, and they are doing something we don't know how to look for. Or the structures are there and we are misinterpreting what we see. The silence from the galactic core is either reassuring or the most terrifying data point in astronomy. That's 10 megastructures, from solar power satellites we could build next century to a shell around the galactic core that would announce a civilization's existence to the entire galaxy. The physics allows all of them. The materials and energy for most of them exist. The only variable is time and the will to reach for them. We are at the very beginning of this story. Subscribe to Cosmic Hives. See you in the next one.